Okay, hello students. Today's class, we finish this design procedure and probably start off with a numerical. Okay, until everyone else joins, I'll just review what we did in the previous class. We just completed helical gears, and we started with the introduction of bevel gears and the steps involved. I think we completed only step one. I'll just review it once again, and we'll start off with the numerical. So this is where we start off when we start with the numerical. So step one is you need to identify the weaker member. This is synonymous to previous two gears which we solved, right? So the step one, you need to source the allowable static stress. Similar to the previous case, allowable static stress from table 12.7. So this is the table 12.7. Depending on what material is given in the numerical, and you need to source the allowable static stress and take that value. Right? So that is about step one, and depending on that, you need to if the number of teeth is not given, so then from you need to refer table. If it is given, if the number of teeth is given, then you can refer to table 12.5, and you can take the value of y. Okay, that is the Lewis form factor, which is required to find the weaker member. You can directly source if the number of teeth is given. You can do this method. Right? If the number of teeth is not given, then you need to refer to a different table. So there is some. I'll show you the table. And once you have both values of allowable stress and the material, that is the form factor, you need to incorporate that in these two, whichever is lesser. So that will be the weaker member, and depending on that, you need to consider those parameters for design in the further steps. Okay, also in the same steps, you need to find number of teeth, that is ze. So first find the weaker member and find the actual number of teeth. So whatever z is will be given, no? So let's assume that is the virtual number of teeth, and depending on that, you need to find the actual number of teeth. And once you find that, in this same step, this y is when the number of teeth is not given. Okay, suppose the number of teeth are not given, then you use these formulae, where you would have assumed some number of teeth, and depending on that, you note it down. Okay, so in the question, whatever number of teeth is given, you note it as the virtual number of teeth, then find the actual number of teeth using the formula. If the number of teeth is not given, you need to refer to table 12.4 and take the actual number of teeth, the assumed number of teeth, and then you need to find y from this formula. Otherwise, if number of teeth is given, you can check this table. Okay, if it is given. If it is not given, then you take it from these equations. Okay, and also in the same step, once you find the weaker member, then you also find delta 1 delta 2, that is the pitch cone angle for pinion and gear. So only one is required, I guess. Not both won't be required. In the further steps when we are doing, I think we need only value for one. Right? So one means one is for opinion and two is for care. So we need these values also. So a few steps are added when compared to the previous helical and the spur gear. A few steps extra are added into the step one. Okay, I hope you have the screenshots of these tables. So these will be required once we start the numerical. Yeah, these are the formulae which you use to find the delta 1 and delta 2, that is for pinion and gear. If it is acute angle bevel gear, so this data will be given. Theta will be given in the numerical, or you can check it out with the data handbook, which I showed you before. So once we go to the problem, I think it will be more clear. Also, this is for obtuse angle and right angle. Okay, you can check out these these numbers. You can take a screenshot at this point where if it is obtuse angle bevel here, where theta is greater than 90 degree and theta is exactly 90 degree. Theta is exactly 90 degree. You use. So these are the miter gear type, which I told you in the introduction part. Right? So this is step two. Step two is as usual, same thing. You find the M, that is tangential tooth load. How do you do that? Is step one, similar to what we solved in previous two modules, the FT. Okay, the tooth load, the generalized equation for tooth load, which is given in power PCS by V. Velocity formula is not there in the uh, data handbook. You just have to by heart this. So I hope you have it by now. And for this thing, we use the parameters here for the weaker member, D and N. No? We use the parameters for weaker member. Then for service factor, you refer to table 12.8. That 12.8 is this thing. So this also we have used in both spur and helical, depending on the shock conditions, type of load, and how many hours it is used per day. Okay, so depending on these two, whichever is given in the question, then we source that information. And part two, so there are two parts similar to the previous. Part A is the generalized equation. Part B is using the Lewis equation. So the Lewis equation here is again different. For spur, helical, bevel, and worm, this Lewis equation it changes. So these are empirical formula based on experiments. So this formula is also here different. So you can see some new parameters here like L. Okay, L is new. It was not there with us before. So what is this L? Is it's the pitch cone length. Okay, it's the length of the complete cone. You can check out the diagram which I showed yesterday. So L is the complete length of the cone which is complete. So that's the value of L. For that we have the formula also. So CV again for bevel gas it is different. Okay, and here it is depending on the type of cutters used, whether it's a generated teeth or used cut by form cutters. So depending on cutters, it is given. So in the previous two, it was depending on velocity, but here it is depending on the type of cutter. And width of the gear. So we have a number of values here. So on an average, I think we'll take around 7, 8, or there is no condition given on which we can assume these values. So we'll do that. We'll set a standard when we start with the numerical. So this is the cone length distance I was talking about. So this formula we can use depending on what data is known to us, whether the diameter or is given in terms of diameter only. Okay, so depending on diameter and or the delta value, this is the cone angle, pitch cone angle. And this is the recommended module series for in case of this bevel gears. So you need to refer to this table and specify the ones which are there. So you can see modules are starting with 1. So here we don't have any problem in dynamic approximation and stuff. So we can start off with 1 and stuff. Whatever we get in the numerical, we'll finish it off. Then yeah, the gear proportions. Proportions are diameters. This is the next step. That is the proportions or dimensions of the gear. And again, this is the easiest one. You just have to refer to the formula here and the module, and then start off with the just substitution. Once you find the module, no, just substitute this here, and you can go ahead with solving. Right? So that's how it works. A pretty simple step. So step 4, dynamic load. The dynamic load formula, I think is almost similar to what we done in the spur gear. So this similar formula which we used in spur gear. Okay, this is easier compared to bevel. And for C value, so this is FT which we get from the previous step. K3 is given just below the this formula. And C, only for C we need to source the data. B, pace with whatever we take, velocity is found in step 2. So only for C, so maybe we have to interpolate using the error values here. So whichever error values they come around these values, you need to source for the particular angle, and then depending on type of cut and module, you need to source the error. So here again, you need to note that module is starting from 4. So even if you take 1, 2, 3, so you may not find healthy value of error here. So therefore, let's try to keep the module above 4. Okay, we'll try that. We'll start from 4 itself, because here it poses a problem once we find module 3 or something. So last step, where load. Where load is a little bit different. This is delta. So delta 1. So it is directly delta 1 or D1. So if whichever is a weaker member, we'll use that particular data. And this is where ZE comes in picture. Check it out, ZE. So this is the actual number of teeth which we found in step 1. So although the number of teeth, if it's given in the question, so don't use that. That is the virtual number of teeth. You need to find the actual number of teeth and substitute that value here, right? That's how it works. So it is also given just below the formula. This not to worry about this thing. That is given just below this formula here, right? So after this, you use this condition for safe design, as for static stress, and get the value of k, just like the previous numericals. So once you get k, we'll refer to this table here. So for that particular value of k and that particular angle, and for the particular material, whichever is given in the question, we'll just recommend the hardness numbers. So that is about the designing of this bevel gear. This is the last step. So it's similar. We have 5 steps in helical and this gear. Right. So that's it. Those are the 5 steps which will be followed in all the numericals. Just read the question properly, and you'll know what to find and what to do. Design means you have to design the whole thing, like the dimensions and all those stuff, right? So, okay, check out this first problem. This is bevel gear. So bevel gear here, uh, he may not give bevel gear. So he may give like intersecting axis, intersecting shafts, like that. Okay, non-parallel intersecting shafts. So that also might be. Let me change this additional data. So in this question, instead of bevel gears, also might be given as non-parallel and intersecting shafts. Okay, so this data may also be given. So instead of directly telling you to find giving you the data bevel gears, we would give non-parallel intersecting shafts. Also, we might confuse you like the power or no motion has to be transmitted at an angle of 90 degree, okay, or perpendicular to the axis of the present shaft, or even we may give for a differential. So mostly these gears are used in automobiles, right? So we have the drive shaft, which is transferring that power in perpendicular directions. So instead of directly giving you bevel gears, we may ask you that the gears are transmitting power in perpendicular directions. In case of automobile, drive shaft and the wheels, so like that. So something like that we may confuse. Okay, so rest of the things are all similar. You have to come to know about what type of gear it is in the first line itself. Okay, so this might be given, might not be given. You just check out what kind of application is there and what additional keywords are given. So depending on that, you decide which gear it is in the beginning itself. Okay, so that's important. Okay, now this is connecting two shafts at 60 degree, and this is one more information which can be sourced 60 degree. So no other questions which we saw previously was an angle given between connections, right? So this is given connecting two shafts at 60 degree. So you can start noting down the data in parallel. Go back to the right. So this is data given is initial theta is given. Okay, where's my theta? So theta is a 60 degree. Right? So that is the initial data. So this is theta. Theta is nothing but the angle between the two shafts. So you have the diagram in the data handbook. You can just check it out. So theta is nothing but the angle between two shafts, and the gears are alloy steel of case hardened type. So gears, he says, gears means both materials. I guess no other material is given. So therefore, material is also given. So material for pinion and gear is the material alloy steel. Alloy steel of case hardened. Case hardened alloy steel for both pinion and gear. So both material are same. So this makes our problem simple, right? So this problem is simple. How? Because we already know this. The weaker member is a pinion. So that's how it is simple. Okay, we don't need to find Lewis factor for gear, right? So that's how it is cutting down. So both are same material, then automatically pinion is weaker, and they are precision cut with form cutters. So these two data is also important for us. So remember, form cutters, the value of CV was important, and for precision cut to get the error, this is important. Okay. So let's note that down. So it is precision. It is precision cut, and it is form cutters. Cutter. And for this data is given, this will be useful for us. Then the gear ratio is 5:1, means it is N1. Gear ratio means N1 over N2. Okay, so this is N1 over N2. Okay, so N1 over N2 is 5. Is also equal to say Z2, Z2 over Z1. Right, so this is our velocity ratio. Next, what else is given? The power transmitted is 30 kilowatt. So power P is given 30 kilowatt. Then 900 RPM of the pinion. Pinion means it is N1, right? So N1 is 900 RPM, and the teeth are 20 degree FDI. So FDI means it is a full depth involute, right? So 20 degrees full depth involute type. This 20 degree full depth involute. Okay, then number of teeth on pinion is given. Number of teeth of pinion means it is Z1. Pinion is Z1. You can see that Z1 is 24. So note here I'm noting down at Z1 itself. I'm not writing as ZE1. Okay, so this you take it as virtual number of teeth. So assume the customer or someone is giving you the number of teeth which are required in a spur gear. Okay, equivalent to spur gear. That's why you note Z1 as 24. Don't note it as ZE1. So note it as a virtual number of teeth itself. Okay, so ZE1 we'll find out later. This is Z1 24 suggests suitable hardness. So it is required to find the BH, right? So it is required to design the gear. We'll start off with the solution. So solution step 1 is to find the weaker member, right? So also in the same step, we need to find delta 1, delta 2, right? ZE1, ZE2. So all these things also let us note down. Also find, let's say, let's call this ZE2, then ZE1, then delta. Delta. Use this. Delta, delta, delta. Oh, it's here. Also delta 1 and delta 2. So along with finding the weaker member, we'll also find these parameters because in the future they'll be required, right? Okay, now let's go to the PPT. Okay, step 1. So from table 12.7, we need to take out the material. So material is given. Let's take the material. Okay, so material given was what is the material? Material was alloy steel, case hardened. Do we have alloy steel, case hardened? Oh yeah, we have alloy steel, case hardened. So you can check out here. So we have that alloy steel, which is case hardened. The value is 345.2. Okay, here. Okay, alloy steel case hardened. Allowable stress is 345.2. Let's note this value. So it is 3. So there is sigma D1, sigma D1 written as subscript is equal to the same value. Sigma D1 is equal to D2 is equal to 3 345.2 345.2 Newton per mm square. Okay, so this is, since both material are same, just after this step, I can write that. I'll write that also. Since both pinion and gear are of same material, you can say pinion is weaker. Hence, design is based on pinion. So design is based on pinion. So whichever is the weaker member once you have got, since both are same material, you decide that pinion is the weaker member. So we have found the weaker member, but we also need to find these values here. Okay, so for that, I will go back to PPT, see what it says. Okay, so number of teeth is known, right? So we can take out the value of y for pinion and gear. Since we have already found that pinion is weaker, we'll take only for pinion. Okay, so but the number of teeth on this is also required. So let's copy this. This is the velocity ratio given in the question. So using this, so you can find N2 and both Z2, N2 and Z2. So we know N1 is 900, right? So also Z1 we know Z1 is 24, right? Right. So with this we can find what is N2. So what is N2 and Z2? Just tell me the value. N2 and Z2. So once you find N2 and Z2, we can go on for finding values of y1. Only y1 is required for us. So okay, y1. Why only y1? Because we already found out that pinion is weaker, right? So y1. Let's go back to the table. Right. Y1 Z1 is 14. Okay, so for 20-degree full depth form, it is 0.88, 0.088. Okay, so we can just take this value from here. Since the number of teeth is given 14, take 0.088. So 0.088. So this is from table. What is the table? 12.5. 12.5 again for Z1 equals 14. Do that. So what is the N2? Everybody found out? Is 900 or 5. Okay, let's say 180 RPM. It's not required actually. And Z2, 24 times 5 is 120. 122. So we have Y1. This will be needed in the future. So let's find ZE2 and ZE1. Let's go back to the PVT. So we already found this. We already found that pinion is weaker because both are of same material, and value for YP will be usually lesser than that of gear. And this is what we use for finding the actual number of teeth. Okay, ZE1 is Z1 by cos of delta 1, but we don't have delta also, right? So in order to find ZE1, we need to find delta 1 and delta 2 first. So that's fine. So this is omitted because we already have the number of t. Okay, for delta 1, delta 2, we need to use these formulae. So what we have is theta. So theta is exactly 90, right? So that is right angle bevel gas. Okay, so this if theta is 90 degree, you need to take these formulae. Okay, so it is check it out here. It is just 1 by I. I here is velocity ratio. Okay, usually it is Z1 by Z2 is 1 by I, and tan delta 2 is I. So we can take these formulae here. Use the velocity ratio 12.32 A. Okay, let's do this. We have tan delta 1, tan delta 1. Do this in subscript. So tan delta 1 is equal to what? For right angle bevel gas. So this also we need to note. Say for theta. Theta is for the right angle bevel gas. So this is theta. Now, theta equal to 90 degrees. 90 degree. Tan delta 1 is equal to 1 over I. 1 over I. 1 over I is nothing but the velocity ratio. So that means it is just 1 over 5. Okay. So let me put this here also so that you're not confused. So this is I. I equals I is nothing but the velocity ratio. So from this we can come to know about delta 1. Okay. So delta 1 will come to know from this. Also tan delta 2. This the equation number also I'll give you. This equation 12.32 A. 12.32 A. Similarly, tan delta 2 is just I. So it means it is 5. So from this we can find directly delta 2. To find delta 1 and delta 2, in the meantime, I'll go back to PPT, and step 1 is not yet complete. I need also to source this information, this thing. I need to find actual number of teeth for that particular bevel gear, right? So these two also I need to find out. Okay, so let me do this. So ZE1 is Z1 over cos delta 1. So this is given in equation. Okay, 12.5 C and D. So ZE1, just copy from this. So this we'll need for step 2. Sorry, step 4, step 5. So ZE1 is Z1 Z1 by cos delta 1, right? So that was given in equation. So this data is required for the fourth step. Z1, we already know Z1 14 reverse delta 1. So 1 over 5 and tan inverse of that. Okay, delta 1 we have um, 11. Okay, we have 11.31 degrees. And what about tan uh, delta 2? Wait, theta is 90 degree? Oh, theta is 60 degree, not 90 degree. Oh, okay, theta is not 90, it is 60. My mistake. Theta is 60, which means these are not same. So it is acute angle then. Theta for this is acute. So you need to take these formula, not for right angle. My mistake. Theta is 60 degree, not 90 degree. So that means these formulae don't hold good. You need to source these formulae here. Okay, you can either, or you can take this sine theta by, I was looking, the same thing. So let me take this sine theta by I plus cos theta. A small mistake. Delta 1, delta 2 are not these formulae. Okay, so tan delta 1 is this sine theta by z2 by z1, which is nothing but I. Right, this sine theta by, let's say, I plus cos theta. So this is 29a. 29a. So be careful while taking this. So 6 became 9 in my case. Um, Let me do this once again. Okay, the same thing. This here it is I'll inverse this. So this is 1 by I. So this here is equation B. Okay, a small mistake can change a lot of things here. So theta is 60 degrees. So therefore use this formula here. So theta here is, let's say here, let me put tan. I'll just replace this by tan. There is tan inverse of this whole thing, where theta is this angle here, 60 degrees. Okay, there is no theta. Right. So this will give us our delta 1. And I again replaced by 5. Okay, so same thing we'll do for this here. It is tan inverse of this entire thing, delta 2. To find this, we are doing this to find delta 1 and delta 2. It will be required in later steps. Just copy this again. Almost there. Right. Okay. So this much is there. So we'll find delta 1 and delta 2 from this equations here. Okay, let's find delta 1. Anybody found delta 1? Post it in the group chat. we'll use that data to find ZE1 and E2. This is the actual number of teeth in the helical gear. It is no longer 140 and is no longer 1. It's 120 number of teeth. Okay, anybody found out value of delta 1, delta 2? Okay, let me check. 960 over 5 plus cos 60 and tan inverse of that. Okay, I have 8.95 degrees. So you can check the answer. Then delta 2 is sine 60 over 1 by 5 1 by 5 plus cos 60 and tan inverse of that. So I'm getting this around 51.05 degrees. Okay, so I have delta 1 and delta 2 now. We're still in step 1. So delta 1, delta 2 are found. So let's use this. So cos of this angle here and cos delta 2, what we have got here is this value. Okay, these are cone angles. The delta 1 and delta 2 are nothing but pitch cone angles of pinion and between the shaft and the the pitch diameter till the center of the teeth. You can check out the diagram. The diagram is clearly mentioned in the red handbook. You can visualize over there. Okay, so I'm getting ZE1 hey, ZE1 is 24. Oh, 24 only. Okay, this is 24, not 40. 24. That means it is 24 divided by cos 8.95. Okay, so this and I'm getting 24.3. 24.3 and this is 120. Oh, not put the cos where it is cos 120 over cos 51.05. So this I'm getting 190 90.9. Let me just approximate this. So I'll make it 25 and this let me make it as 191. Right. So this completes step 1. Okay, this completes step 1 of this numerical. That is, step 1 is quite lengthy when you came at transfer between helical and spur gears. But you can see most angles are found. So this delta 1 and delta 2, I'll show you in the PPT where it is. Go back to introduction. I had put that. Oh yeah, it's here. See, this is delta 1. So delta 1 is the angle between this meshing teeth here, okay, and between the axis of the pinion. Okay, that is delta 1. So this angle what we have got here is 8.95. degrees, and delta 2 is here. So that is gear axis and the corresponding meshing teeth of that gear. Okay, or the pitch line. Okay, the pitch line of that and the center line of the shaft. So that is delta 2. So you can visualize that this is bigger. The gear is bigger and the pinion is smaller. And since pinion is weaker, we have taken that particular. So these are the number of teeth, actual number of teeth on the bevel gears. So both of these gears. So this gear will have like 25 teeth, and the gear here will have 191 teeth. So that is the visualization. We can see that. Okay, between this 25 and 191, right? So you can see here theta value for less than 90, greater equal to 90, greater than 90. It's the next statement. So, yeah, greater than 90. There are different formulae. We don't get confused with those formulae. And yeah, just as I got confused, you may also get confused some point. So be careful while choosing the particular formula, right? So yeah, step one we are done. So step two we'll start off with in the next class, in tomorrow's class. So step one was a little bit lengthy. What I've seen was we found various other parameters also, right? Okay, so yeah, that's it for today's class.